Can you hear me, guys? Okay, so I think many students attend the in-person lecture. And unfortunately, the Zoom setting was changed in this classroom, and I cannot set up Zoom correctly, not correctly, normally. What's the matter? 자꾸 세팅을 바꾸나? Okay. So I recommend you to attend the in-person lecture actually. Okay. So because it's not easy to set up Zoom. Okay. In the previous class we covered the speculative execution and then register renaming, then some other techniques in the out-of-order processor architecture. Actually, this is the very important topic because the modern processor uses this out-of-order processor architecture. So actually, the modern processor employs out-of-order processing and speculative execution and superscalar. So by combining these techniques, we can improve the performance of the modern processors. So it's very important to understand how out-of-order processing is working in the this processor architecture. So actually, in order to enable a speculative execution, the processor includes the reorder buffer and then the prediction units like branch prediction buffer and branch target buffer, and then register alias table. And then we also learned that the register alias table is changed to support the register renaming because in the previous class I explained that the operand data can be stored in the many places such as the issue queue and then reorder buffer and then also in the register file, but it's the waste of hardware resources. And so in order to reduce the waste of hardware resources, so we actually computer architect applies register renaming. So which means that the number of physical registers is larger than the number of architectural registers. So actually, every data which is used by instructions is stored in the physical register. But the software, like instruction, use the architectural register number, and then this number of architectural registers is defined in instruction set architecture manual. So I frequently use this instruction like add x1, x2, x3. So if you see that this instruction, then you can find the register numbers in the destination register or the source registers. And then these numbers, the register numbers are architectural register numbers. So actually the software uses architectural registers, but in the real hardware. So in the real hardware, so actually the number of architectural register is fixed. Like in the RISC-V, we just have 32 architectural registers. But actually, in order to implement the out-of-order processing, we need to use the larger registers, the larger number of registers actually. So which means that in order to avoid the war hazard or wow hazard, actually it's like the add. I repeatedly explained the add and then. So if we see this add x1 and then sub x1, so actually if we see that these two instructions, so architectural registers are the same, but we already know that these data have different values. So which means that we need to distinguish these X1 by add instruction also and X1 by sub instruction. So in order to avoid the wall hazard or wall hazard, actually we require more registers, and then actually in the Thomas-Law algorithm, the Thomas-Law algorithm has tags, and then the register data is stored in the issue queues. So we can distinguish the different registers, different data, even though the architectural register number is the same. So we can distinguish these different data with the tag in the Thomas-Law algorithm. And then in the Thomas-Law with speculation, we distinguish these different data with the ROB number, ROB entry number. So it is because when this instruction is dispatched in the processor, the ROB entry number is registered to this instruction. So which means that we can distinguish different instructions and then different destination registers with the ROB entry number. So we can use ROB entry number as like the renamed register numbers. But as I explained, the disadvantage of the speculative Thomas-Law is that the register, so actually the register data is found in different places, like the issue queues and the architecture real register file and the ROB entries. And so it's some kind of a waste of hardware resources. So actually we can apply the register renaming. So register renaming is that actually every data updated by actually the register data. So every register data is stored in the physical register, but the size of this physical register is larger than the actual architectural register. So which means that we can store more data, which means that like add X1 and then sub X1. So even though this architectural register number is the same, but this data can be stored in the different places, like P1 or P2. It's a physical register number. So with this technique, then we can use the larger physical registers, and then we can distinguish the different data by different instructions. So which means that we can apply the register renaming with the larger physical registers. Okay. It's similar to the virtual memory, right? The virtual memory, so actually the software just access the virtual memory space. So it's a fantasy world. But real data is stored in the physical memory. So we just adjust some mapping information between a virtual memory space to physical memory space. This is the virtual memory. And then the same technique can be also applied to this processor area. There is larger physical registers, and then smaller architectural register. It's like some virtual register, and then there is a larger physical register file. So this architectural register can be mapped to some different places in the physical register file. So this is the register renaming. So with the register renaming, then it's some very small disadvantage. So if we apply the register renaming technique, then we need the additional pipeline stage called register fetch, because all required data is found in the physical registers now. So physical registers need to provide the required occurrence to the instruction when the instruction is issued to the execution engines, like execution units. So it means that we need the more stage, one more pipeline stage called register fetch. And then, so it's like some advances in the process architecture. So which means that in the this out of the process architecture, so this processor does not support data forwarding, right? So what is data forwarding? In the static pipeline architecture, the data can be forwarded from the output of the ALU or output of data memory. But so in this out of the processor, like the speculative Thomas law and register renaming. So this architecture does not support data forwarding. Like so, in order to support the data forwarding, we can apply the speculative scheduling. So what is the observation that can enable speculative scheduling? The observation is that usually the execution engines or execution units have a fixed latency. So it's a fixed latency. The latency is the same. So which means that if an instruction is issued to the execution unit, then the result is generated at some fixed latencies. So that's why we can apply the speculative scheduling. So which means that if a dependent instruction is issued to the execution unit, then we can know when the result is out from the execution unit. So and then we can forward this result to the another instruction. So this is the speculative scheduling. So it's a little bit complex, but we can apply. So with the speculative scheduling, then we can reduce the latency of a single instruction. See? So it's some various techniques of some prediction. So actually, in the processor, many prediction techniques are applied. Like so, in this course, we already learned about the branch prediction, which means that the result of a branch can be predicted by hardware. So another prediction is the memory disambiguation. Okay, so which means that if the former instruction is a store, like a store word, and then the following instruction is the load word, this load word cannot be executed because the address of the store, if the address of a store instruction is known, because if this address is the same, then this load instruction cannot be executed before this store instruction. But we also assume that, even though this address of the store instruction is unknown, so we can assume that the load address of this load instruction is different from the address of this store instruction with the very high probability, because the main memory is very large. So it means that the address of the different memory data transfer instructions may have different addresses. Okay? So with a very high probability. So this is the memory disambiguation. But if this assumption is missed, we need to roll back the execution of this load instruction. So this is another prediction technique in the out of the processor. And then another technique is the return address stack. Okay, so return address stack means that so we frequently use the function or procedure. Okay, so which means function or procedure is some independent group of instructions, and then we can return from these functions or procedures. So this return address is stored in the return address stack, but it's also the predicted address. So which means that if the return address stack is full, you can store these return addresses on this stack. So then the predicted return address can be different. And then another prediction is the value prediction. Okay. So value prediction is that actually our program has some frequent data values like zeros or ones. Also, like if we see some iteration loop, then we can say we can expect that I is increased like by 1, I plus plus. So actually, in the computer processor, we can observe many predictable values. So value prediction exploit these observations. So which means that even though the value of the operand of this instruction is unknown, like this other source registers, then we can predict the value of this instruction. Then we can use the predicted values for a certain instruction. So if this prediction fails, then we can roll back execution of this instruction. Okay. So it means that manipulation techniques can be applied to our processor architecture, because now our processor can roll back the execution of instructions before the instruction is committed to the processor. Okay, because our processor has ROB, and then if the prediction fails, then we can roll back the execution. So it means that we can apply some other prediction techniques in the processor, but in order to apply the some prediction techniques, then the hit rate. The hit means that if the prediction is correct, so hit rate of this prediction techniques should be very high. So if the prediction hit rate is around the 50%, you cannot apply these prediction techniques. But if you see these several prediction techniques in the processor architecture, like branch predictor and memory disaggregation, return stack, so we can say that the hit rate of these techniques are very, very high. It's around higher than the 95%. So if that's why we can apply these prediction techniques in our processor architecture. And then the good thing is that if we apply the prediction techniques, then we can improve the performance because hit rate is very high. And what is the disadvantage? Disadvantage is that the hardware architecture gets more complex. So, and then if the hardware architecture gets more complex, then this hardware will consume more power. Okay, so architecture is very complex, then hardware will consume more power, and this is the kind of cost of the processor architecture. So the goal of our research is to improve the performance while reducing the cost of our computer system. So if we use the very complex hardware, then the cost of this processor will also increase. But so that's why we need to check the performance and the cost when you apply the new idea. So I mean, you can compare the performance improvement and then the cost improvement, cost avoid like this. So if you invest some resources, like so that means that the cost of the processor may be increased by 5%. But if the performance can be improved by more than 5%, then we can apply this technique. Like performance, if the performance can be improved by about 10%, then it's good to apply our ideas on the processor. But if the cost is higher than the performance improvement, then we cannot apply our ideas on this processor architecture. Okay, so value projection and then summary of out of order processor. So actually, I shared some out of order processor review, and then in this review, I explained the out of order processor architecture in Korean. So I shared my YouTube link. Also, during this semester, I also explained some out of order processor architecture in Korean to some different different course. So I also shared the YouTube link that, and then that includes some videos which explains the out of order processor architecture in Korean. Okay, so if you have trouble understanding how out of order processor works, then you can watch the shared video. Okay, so this is the very important part of this course, and then also the modern processor. The most of the modern processor employs is out of order processor architecture. Okay, now some just renaming and speculative scheduling. So, and then another technique is the superscalar. So superscalar. So actually, until now, we learned that our processor fetch one instruction per clock. So that's what we learned in the undergraduate course also. So, but if we see the architecture of out of the processor architecture, then we can find that our processor has multiple execution units, like integer unit, and then floating point unit, and then memory unit. So if we see the number of execution units, then we can know that, oh, our processor can execute actually at least three instructions per clock, because there are multiple execution units. But what's the problem? The problem is that we learned that our processor fetch a single instruction per clock. So how can we improve the performance in this case? So now, we are learning how to improve the performance with instruction level parallelism. What does that mean? We can increase number of instructions which are being executed in a processor, then we can increase the performance of our processor. So we are learning how to improve instruction level parallelism, so which means that we want to increase the number of instructions which are being executed in a processor. Okay, so the problem is that we learned that until now we learned that only single instruction is fetched per clock. And how can we? But our processor has capability of executing multiple instructions because this processor has multiple execution units. So what is the possible idea? We can fetch multiple instructions per clock, and then which means that we can exploit the multiple execution units, and then these multiple execution units can execute multiple instructions per clock. This is the superscalar idea. So in the superscalar processor, this processor fetch multiple instructions. Like, so for example, if we use the 16-way out of order processor, which means that this processor can fetch 16 instructions per clock. And then these fetched instructions are included in the instruction fetch queue. And then we need to improve also. So first, we can fetch multiple instructions. Then we can include these multiple instructions in instruction fetch queue. Then which part should be improved? Actually, the superscalar idea is simple. Then the implementation is a little bit complex, so which means a little bit tricky. So think about this timing table of the out of order processor. So actually, we cannot find any instruction fetch stage here because we assume that the instructions are already fetched in the instruction fetch queue. So in order to support a superscalar, then we need to improve dispatch or decoder engine. So which means that, so in this example, you can find that a single instruction is dispatched every clock cycle. But in order to support a superscalar architecture, then we need to dispatch multiple instructions. So which means that we need to decode multiple instructions. Okay. So which means that the ROB is also updated. ROB also, the multiple instructions should be registered in ROB. Also, the register alias tables also need to handle the multiple instructions. So actually, the idea is superscalar idea is very simple, but in order to support the superscalar, then our hardware like the register alias table and then also the registers, physical registers, and then ROB need to support multiple instructions. So it means that higher bandwidth. Also, the common data bus. So we assume that only one instruction is delivered to the common data bus, but in order to support the superscalar, common data bus also need to deliver multiple instructions. So which means that the bandwidth the architecture should be increased. So it's not an easy problem. It's not easy, but the most of processor now supports the superscalar architecture. Okay. Also, another issue is that we already learned that the size of the basic block is about 4.5 for the normal applications. So which means that if a processor fetch 16 instructions, then which means that this group of instructions may include 2 or 3 basic blocks. So how can you handle these multiple basic blocks? So which means, we need to fetch, so actually the processor needs to fetch 16 instructions, but these 16 instructions may include 2 or 3 branch instructions. So what does that mean? What's the matter? So if the branch is it's not taken, then we can fetch the very next instruction. So it's not a problem. But problem is that if the branch is predicted as taken, then which means that for the first 5 instructions, we may fetch some instruction streams here, and then at the last instruction of this basic block, the branch is predicted as taken. So which means that after this instruction, we need to fetch different instruction streams, like from the different program counter, the target of the branch instruction. So that's another issue of the superscalar processor. So actually, the technique is very complex. So also, this is also some kind of research field. So like that. So actually, in the early 2000 or the early 2000, computer architects focused on this issue, like the instruction fetch issue for some predict instruction fetch issues in the superscalar processors. Okay. So actually, the architecture is very complex, but recently, so actually we can improve the performance of a processor with the thread level parallelism. So So actually, in the first, not the first, maybe it was second or third class, I explained that recently we live in the multi-core era, which means that with a single processor like a uniprocessor, it's very hard to improve the performance. So which means that we have improved the performance of the single core processor with some advanced semiconductor technology, also advanced architectural techniques. But now it's very complex. The architecture of the single core processor becomes very, very complex. So it's not easy to improve the performance. And so another issue is the saturated semiconductor technology. So we are saying that the Moore's law is ending, so it's being ended. So which means that we cannot use the advanced semiconductor technology. So it's not easy, So nowadays, the semiconductor technology is very critical for the economy of some nations. And then, actually these semiconductor technologies are led by several nations like our nation, Korea, and then Taiwan, also United States. But it's not easy. So and then also the cost is the problem. So modern processors now support the out-of-order processing and then speculative execution and then superscalar. So with this technique, then we can improve the performance of a single core processor, like uniprocessor. But so nowadays, this performance improvement is just saturated. So we need to find some new ways that can improve the performance of our processors. So after the early 2000s, we can apply the multi-core architecture. The multi-core architecture exploit the thread level parallelism. Okay. So also the multi-threading, so like the hyper-threading. So we can also improve the thread level parallelism. So nowadays we can apply to some multi-core architecture or multi-threading or thread level parallelism in our processor architecture. And then recently we can also focus on the domain-specific architecture. But it's very important to understand how the modern processor works and how the modern processor exploit some architectural techniques to improve the performance. Okay. Okay, so I already also. And then let's think about the CISC architecture. So I believe everyone knows that x86 is the CISC. It's a complex instruction set computer. And then, another very popular architecture, ARM instruction set architecture is the RISC. And then also recently, the RISC-V ISR is VRO. So actually the RISC architectures RISC instruction set architecture was developed by very famous computer architect, so David Patterson or John Hennessy. So they are very famous. Actually, they are legendary people in computer architecture field, And then they wrote the very popular textbook in computer architecture, like Computer Organization Design, very popular book. So actually, we can compare the CISC architecture and then RISC architecture. CISC, C of CISC means the complex. So which means that the instruction set architecture is very complex. But if you see the RISC architecture, R means the reduced. So which means the instruction set architecture of a RISC computer is it's simpler than the instruction set architecture of a CISC computer. But what's the benefit of the simple instruction set architecture? What is the benefit? The benefit is that the decoder, hardware decoder of this processor becomes simpler. So we can use simpler hardware decoder. Okay, so which means that the computer, the architecture of the processor can be simpler. Okay, so actually the RISC architecture is, so if we use the RISC instruction set architecture, then we can build a more efficient processors. But we already know that the most of desktop computers or laptop computers have include the Intel or AMD CPUs, and then Intel or AMD CPUs support x86 architecture. The x86 is the CISC architecture. It's complex. And then if you read the instruction set architecture manual of the x86 ISA, then you can find the, oh, it's very dirty, because the x86 has very long history, and then it starts from the CISC type architecture. Also, the Intel or AMD need to support the backward compatibility, which means that if some application is compiled with the x86 compiler, maybe 30 years ago, then modern processor needs to run this binary file without any new compilation. So that is the backward compatibility. So which means that in the old age, the x86 includes the very inefficient instruction set. But Intel or AMD cannot abandon this inefficient instruction set in order to support backward compatibility. So which means that instructions are very dirty, the x86 architecture, but our modern processor also needs to support the very complex and dirty instruction set. What's the problem? Because the x86 needs to support the very complex instructions, the hardware architecture of the x86 processor can be more complex than the RISC type computers. And then it's not good for the performance or some cost of the processor. So what's the problem? So we already know that x86 CPUs are less energy efficient than the ARM CPUs. So actually ARM is developed for the mobile or embedded processors. So ARM has the higher energy efficiency, but you know, the x86 exhibit a higher performance than ARM CPUs. How? Because inside of the x86 architecture, which means that the process architecture of the Intel or AMD CPUs also very similar to the architecture of RISC processor. So which means that even though our x86 CPUs support the very complex instruction sets, these instruction sets are decoded into very simple RISC type instructions inside of a processor. And then actually the processor executes the decoded simple instructions. That's how the x86 exhibits the very powerful performance compared to the ARM CPUs. So actually, if you see the inside of the x86 processor architecture, then this x86 processors also have very similar architecture of RISC type architecture. So which means that it's very similar to the process architecture of ARM CPUs. RISC-V CPUs. And then the x86 CPU supports some architectural techniques like the out-of-board processing and then the register renaming and speculative execution. Then they can improve the performance. So actually, inside of the processor that will support the RISC-type instruction, but the RISC-type instructions are decoded into multiple RISC-type instructions inside of the CPU. So actually, the x86 architecture can fetch the multiple instructions here based on some complexity of the instructions. Then these multiple instructions can be decoded into also some instructions can be decoded into multiple simple instructions like this. And then these decoded instructions are also included in the micro ops queue. And these instructions are dispatched. So this is the modern architecture of the x86 processor. Okay, so x86 supports the microcode, and then with this microcode, then some complex instructions are decoded into simple instructions. So by doing this, the x86 also x86 processor also exhibit high performance and some power efficient processor architecture. Okay, so that's why even though this instruction is executed in x86, the performance is very high because the modern processors also have RISC-like architectures. So we cannot actually distinguish. So someone may say that if we have the RISC-type instruction set, then performance can be higher. But it actually in the modern processor era, it's not true because most of the processor has RISC-like architecture like this. Okay. Okay, so this is the end of the out of the process architecture. Okay. So, I don't have it. So actually, we will learn about the next topic is the VLIW, and then let's take a 10-minute break. Okay. Okay. Let's take a 10-minute break. So because so we need to cover the next topic. Okay, after 10-minute break. 네, 호환이 안 된 상태에서 이때는 좀 더 이제 깨끗한 프로세서를 만들겠다고 하는데 IA64입니다. 이 IA64가 이제 컴파일러의 도움을 크게 받아서 프로세서는 굉장히 이제 간단하게 만들고, 그 다음에 컴파일러가 굉장히 많은 일을 해가지고 그 많은 인스트럭션을 한꺼번에 돌리겠다라고 이제 설계를 한 거고요. 그게 이제 아이큐니움 프로세서인데 최근에 발전됐어요. 사실 인텔이 계속해서 이제 뭐 유명하진 않은데 그래서 인텔이 계속 밀고 있다가 일단 영맥만 남은 거죠. 좀 살려두고 있다가 2018년인데 17년인가 그때 그냥 안정시켰습니다. 더 이상 안 쓰니까 사람들이 안 쓰는 거. 그러니까 이게 백워드 컴패티빌리티가 문제가 돼요. 그러니까는 좀 이제 중요한 게 이거 항상 좋은 기술이 살아남는 게 아닙니다. 뭐 시장에서는. 그러니까는 사실 이 VLIW나 이제 벡터는 요새 쓰고 있으니까 VLIW나 이제 이런 것들을 보면은 뭐 학문적으로 보면은 뭐 괜찮아요. 연구할 것도 많이 있고 그런데 더 이상 쓰지 않아요. 그렇지만 이제 배우는 이유는 우리가 이제 과거로부터 많은 걸 배울 수 있습니다. 사실은. 요새 이제 좀 프로세서가 지금은 이제 도메인 스페시픽 아키텍처라고 해가지고 또 새로운 프로세서 구조를 또 요구를 하고 있어요. 그 세상에서. 마켓이죠. 세상 마켓 뭐 이렇게 할 수도 있는데, 그리고 우리가 이제 새로운 프로세서 구조를 이제 좀 생각을 할 때 이게 그냥 우리 사람들이라는 것이 그냥 뭐 아무것도 없는 상태에서 갑자기 연구해서 뭔가 새로운 걸 만들어낸다든가 그런 거는 거의 없습니다. 그런 일은 지금은 일어나지 않을 거예요. 아마 뭐 여러분이 연구할 때도 마찬가지고, 뭔가 이제 맨 땅에 아무것도 없는데 그냥 연구해서 새로운 게 나왔다, 좀 본다, 이런 거는 거의 없습니다. 결국에는 그 과거에서 해냈던 어떤 테크닉과 어떤 기술들을 또 이제 접목을 해가지고 또 새로운 걸 만들고 거의 뭐 그런 거예요. 그러니까는 이 VLIW나 이런 것들은 굉장히 이제 좀 수업 듣다 보면은 아 이거 도대체 뭐야, 좀 다르다, 이런 거를 좀 느낄 수가 있을 것 같은데, 또 이제 문제는 또 안 써요. 그래서 안 써요. 이 VLIW를 적용한 프로세서가 없어요. 뭐 그럼에도 불구하고 배우는 이유가 이런 테크닉들을 통해서 어떤 식으로 문제를 해결했구나, 그런 것들을 또 배울 수가 있고요. 여기 쓰인 테크닉들이 이제 또 새로운 이제 뭐 도메인 스페시픽 아키텍처라든지 이런 쪽으로 갔을 때 또 응용이 될 수가 있습니다. 특히 이제 벡터 프로세서 같은 경우에는 뭐 지금의 GPU랑 거의 굉장히 비슷한 구조를 가지고 있고요. 뭐 그렇기 때문에 이 다음에 이제 약간 GPU를 다루긴 할 텐데, 그 보면은 이제 좀 비슷하다는 거를 알 수가 있어요. GPU는 요새 쓰니까, 많이 쓰니까요. Okay, the next topic is the VLIW. So we will learn about the LIW or VLIW. So we will learn about the VLIW scheduling. So what is LIW or VLIW? So if you see that this V, actually V is just means very. Okay, so what is LIW? LIW means that long instruction word. Okay, so what does that mean? So VLIW is some very neat. It's a new architecture, new process architecture, but this architecture is very different from the what we have learned in this course. So in this course, we have learned about the static pipeline architecture, or so the dynamic pipeline architecture, like out-of-order processor architecture. But the architecture of the LIW and VLIW is very different from what we have learned in this course. So it's very a special architecture. So, and as I explained, so actually recently we do not use LIW or VLIW architecture, but so it was uh, researched and studied by some academia and the industry field like Intel. So I think it would be very good if we learned about some techniques or some architectural ideas in LIW or VLIW processor architecture. Okay, let's see the main features of this LIW or VLIW architecture. So what is the basic idea? The basic idea is that so we have learned about the out-of-order processor architecture, but so it's very complex. So which means that the architecture is very complex, and then you have to implement this architecture with some real processor. Then the processor architecture becomes very complex. So which means that we need to invest more hardware resources. Also, so we need to design complex hardware components to implement the out-of-order processor. So which means if the hardware becomes complex, what's the problem? The cost is increased. And then complex hardware also consumes more power. So which means that the loading cost is also high if we apply the out-of-order processor architecture. Also, as I mentioned, so modern processor employs three main techniques like the out-of-order processing, speculative execution, and then superscalar. It's also very, very complex. Okay. So, but So actually, if we see how the software is executed in the computer systems, actually the software is written in high-level language, and then this software is analyzed by compiler, and then compiler generates the assembly code, and okay, and then also when the assembly code is generated by compiler, then we can apply many computer optimization techniques. Okay, so which means that if the compiler knows how the processor works with some instructions, then compiler can apply the optimization techniques. So, for example, if you use the GCC compiler with a GNU C compiler, then we can set up some optimization levels like -01, or 2, or 03. So actually, I believe you were requested to compile the spec benchmarks with the different optimization levels. So which means that compilers can analyze our code, and also compilers can analyze the compiled code, and then compilers can adjust the order of instructions to improve the performance. What does that mean? The performance of computer systems are influenced by hardware, obviously. Also, it was influenced by compilers. So the problem is that the hardware is getting more complex, and then if we apply the more complex hardware, then it will consume more power, and then it will consume more cost, higher cost. Okay, so the idea of the LIW is that idea of LIW is so we can use very simple hardware, like the 5-stage pipeline architecture. The 5-stage pipeline architecture is very simple. And if we use very simple hardware, then we can run this processor with higher frequency, right? Because the hardware is very simple. Also, this simple hardware will consume less power. That's the benefit of a simpler hardware architecture. Then how can you improve the performance? So I already explained that the performance of our computer system can be improved by software and hardware. And then in the software part, if we apply some different optimization levels, then we can improve the performance of a system. So which means that compilers can analyze our compiled code, and then which means that compilers can adjust the instructions in the compiled code. So basic idea is that, we want to use the simple hardware, and then how can you improve the performance? And performance can be improved by compiler techniques. That is the basic idea of LIW or VLIW. Then how can compilers improve the performance? So for example, so why performance matters? So why performance is degraded in the real processor architecture? It is because of hazard, right? Like the three kinds of hazard: data hazard, control hazard, or structural hazard. Because of a hazard, then the performance is degraded. Compilers can improve, also reduce the hazard. So for example, compilers can reduce data hazard by adjusting the instruction orders, which means that if compilers can insert independent instructions between the dependent instructions, then we can reduce data hazard. So that is the very simple example. So which means that compilers can generate the instructions, and then compilers can analyze the instruction like data dependencies, and then also compilers can estimate the hit rate of the branch instructions also, because compilers can generate the iteration loop or if then as branches, and then if we just see our code, then we can also estimate the number of iterations in this for loop code in our high-level language code, right? Like that. So if we see the for I equals 0, I is less than 100, then we can estimate that, oh, in this loop, the iteration number is 100. So compilers can analyze this. So the basic idea of the LIW or VLIW is that hardware is very simple. And then so hardware has some slots for the execution units, like the integer hardware, and then integer hardware 2, and then load, and then store, and then floating point execution units. And compilers can assign instructions to each slot of hardware. Okay. Then how can improve the performance? We can apply the compiler optimization. Compilers can adjust instruction orders. Also, compilers can give some hint bit for the branch instructions based on some behavior of the branch instructions. Also, compilers can apply some optimization technique like the loop unrolling. So these are done by compiler. Okay, but if you hear like some basic idea of this LIW, this idea is very similar to our out-of-order process actually. So out-of-order process also actually dynamically analyze the data dependencies, right? So data dependencies are analyzed by hardware, like hardware in the hardware dynamically, and then based on the analyzed data dependencies, our hardware change the register numbers. So hardware change the architectural register numbers to the real physical register numbers, and then start the data some hazard caused by data dependencies. So with the out-of-order processor, we can avoid some hazard like the wall hazard or wall hazard. So in order to support these techniques, the hardware becomes very complex. So the idea is that this burden is moved to the compiler. The compiler analyze our code, and then very strong optimization technique can be applied. And but hardware has the very simple architecture. So that is the main idea of LIW or VLIW. So this is the basic idea. So I explain about the basic ideas of LIW. The compiler schedule instructions. So we already know that compilers can schedule inside of a basic block, but it's not enough for improving the performance because the basic block size is very small. So we can just find the small number of instructions that can be addressed, the small number of instructions in the basic block. So with this small number of instructions, we cannot apply the compiler optimization techniques. So in order to increase the size of the basic block, we can apply some more aggressive compiler techniques like loop unrolling. Then what is the problem of the loop unrolling? So actually, in the out of the processor, we don't need to apply loop unrolling actually. It is because like this. So for loop is here, and then some instructions are here, and then which is the end of the for loop. So this is actually the branch instructions. So then the behavior of branch instruction is predicted, and then after the wall of this branch instruction, so out of the processor can find more instructions after this branch instruction. But if this prediction technique is not applied in hardware, so I said that the basic idea of the VLIW is that the hardware structure is very simple. So we can use the very simple hardware. So which means that this VLIW hardware doesn't support out-of-order processing or speculative execution and some other techniques we learned in this course. Instead, compiler analyzes some code and then compiler applies the optimization techniques like this branch prediction, or speculative execution. So loop honoring is some main techniques that can be applied by compilers. So compilers can increase the number of instructions by unrolling iteration loops. And what's the problem? We need to solve while or hazard. Actually, the out of a processor, we can solve while or hazard with register renaming. Compilers also can apply the register renaming techniques to solve while or war hazard. Okay, and then compilers can analyze the code. So actually, low hazard is the true hazard, true data dependence hazard. So actually, this low hazard can be easily solved by compiler, right? And then also another issue is the memory disambiguation. So this is another some performance of parallel in the data transfer instruction. And then, so in the out-of-order process architecture, so this memory disambiguation problem is solved by a prediction technique. Okay, and then this is also done by compiler. So like this prediction technique can be done by compiler. This is another technique, the compilation technique, and speculation. So speculation is also handled by compiler technique, like the static branch prediction. So what's the problem? So actually the basic idea of VLIW is that the burden of hardware. So actually these are the burden of hardware of out-of-order processor. So these burdens of hardware are moved to the compiler, the software world. Okay, that is the basic idea of the VLIW. Then how can we apply? So this is some another techniques in the VLIW or VLIW. And then let's see some simple the basic architecture of the VLIW. So this is the hardware architecture of the VLIW. So as I explained, so there are multiple slots for different instructions. So which is very similar to the backend part of the Thomas algorithm, right? In the backend part of the Thomas algorithm, there are multiple execution units, and then instructions are dispatched to the different execution units. So this alignment of instructions and then dispatch of instructions, issuance of instructions are handled by hardware dynamically. But in the VLIW or VLIW, this process is done by compiler, the software. So hardware has the very simple architecture. Like the hardware has some slots for the execution, and then instructions are assigned by compiler. So there are multiple slots or for the different instructions, and then different instructions are grouped into the very long instruction word. That's why it's called the VLIW. So multiple instructions are grouped, and then this large instruction is that it's given to the hardware. Okay, and then each slot has its own static pipeline. So if you look at this architecture, you can find that there are 5 slots here, and 2 slots for load and store instruction, like memory instruction, and 2 slots for floating point instruction, and then 1 slot for integer or branch instruction. So, and if you see the pipeline architecture of each slot, you can find that each slot has the static pipelines, like so decode, like execution, the memory part for the load instruction, and write back. So this hardware is very simple. So it's like the very simple 5-stage pipeline architecture is assigned to different type of instructions. This is the VLIW architecture, and then compiler assigns the instruction to each slot of a very long instruction group. Okay, so long instruction word actually. So how do you fetch this large instruction? Okay, so in this example, the hardware has 5 slots, and then when we learned about the RISC architecture, we assume that the size of a single instruction is about 32 bits for the RISC type processors. Okay, but so if the same size is applied to this VLIW, so like it's a 32 bit, 32 bit, 32 bit, so it's just like the 32 multiplied by 5. It's about 160 bits. So this 160 bits is the size of one instruction group. And then this one instruction group includes multiple instructions. Okay, the compiler assigns the different instructions here. So we can also, the hardware can support the foldings, or also the hardware may not support data folding in this architecture. This is the hardware. It's very simple. Okay? And then compiler needs to analyze instructions, and the compiler needs to assign instructions to each slot. Okay, this is the VLIW. Then, what's the problem? The burden of the code analysis and then some data dependencies are moved to the compilers. Okay, and then this is some example code. Also, the compiler needs to know the detailed architecture of hardware. So that is the problem. So in order to apply some optimization, compiler optimization, then compiler needs some hardware information like the latency, and then the possibility of the data forwarding, also some hardware support for the exceptions or the speculations, something like that. So actually, in this example, the compiler has the latency information in the VLIW hardware. So compiler have some tables like this. So this table shows the instruction production result. So the result is produced by this type of instruction, and then this is the instruction that consumes the result of this instruction. And then this is the latency. So what does that mean? So which means that in order to use the floating point result of the former instruction, then the next following instruction needs to wait 2 clocks. This is the meaning of the latency. So which means that if this is the f add, the floating point add, and then this is another f add, and like so f1, then f1. So we can find the data dependence between these two floating point add. So in order to use the result of this floating point add, then this floating point add need to wait 2 clocks. Okay, and it's obvious, right? But what's the better? Actually, the out of the process architecture or some static pipeline architecture, this data dependency is done by hardware, and then this data dependency is detected, then hardware stores the execution of this instruction. Why? Because it's latency too. Hardware knows that we cannot execute this instruction because the result of this FF is not ready. So this instruction is stored in the pipeline. But in the LIW, hardware does not analyze data dependency. So hardware may need to analyze the data dependency, but this kind of some pipeline control is not supported by hardware. So which means compiler needs to assign instruction like this FAD after 2 clocks of this instruction. So which means that compiler needs to assign instructions after some 2 instruction groups. So what does that mean? The burden of hardware is more the compiler. So problem is over the LIW means that the compiler needs to the detailed information or detailed architecture of the hardware. So this detailed information is used for optimizing instructions in the LIW. So this is another example of the latency here and here and here. Also, branch delay slot. What is the branch delay slot? So delayed branch means that like there's a BQ, and then this is the add, and then this is sub, like that. So problem of the branch instruction is that if this branch is taken, then we need to jump to the target of the branch instruction, which means that the target may be here. So actually, so if the branch is not taken, we can execute the very next instruction like add and sub. So delayed branch slot means that even though in the very simple pipeline architecture, so which means that the branch is taken, and then the method of the branch is reserved in the execution state. It's true, right? The branch can be reserved in the execution state, but it means that then the next instructions are already fetched and they're already located in the instruction fetch stage and then instruction decoding stage. And then if the branch is taken, instructions will be flushed. So that's how the branch is executed in the simple static pipeline architecture. Delayed branch means that even though the branch is taken, some instructions after this branch instruction is not flushed. You understand? So how can we apply this delayed branch? So for example, in this example, the delayed branch delay slot is 2, which means that after this branch instruction, 2 instruction groups will not be flushed regardless of the result of a branch instruction. This is the delayed branch, which means that this is the add, and then this is the sub. even though this branch is taken, these two instructions are not flushed in the processor. Is that possible? Oh. So for example, so actually it's very it's not so it's branch instruction. So it's going just to the target of the branch. But if we apply the delayed branch flag, then some next instructions are not flushed, even though the branch is thick. Which means so like so it's not a good example, but we can write the code like this if the delayed branch is applied. So for example, like this. So if this is the original code, like sub and add, and this is the BQ, right? So like x1, x2, and then this x3. Okay? So if the formal instructions of this branch instruction is not related to the branch instruction, so which means that these are independent instructions, then we can move down these instructions to the after branch instruction. That can be possible, right? Because these are independent instructions. So add sub and BQ, and then if these instructions are independent with the branch instruction, then we can move down this add instruction and sub instruction at the branch instruction. And then if the delayed branch flag is supported, then two instructions after this branch instruction is always executed. So which means we can move down the independent instructions at the branch instruction. So if the delayed branch is supported, then we don't need to flush these instructions, even though the branch instruction is taken. That is the delay. It's good. But that's the problem. So actually, we do not write code like this, which is if there is a branch instruction, we going to find the independent instructions before this branch instruction. So which means even though the delayed branch flag is supported, then if we cannot find any independent instructions before the branch instruction, then we cannot move down these instructions after the branch instruction. That's the problem. So problem is that the basic block size is very small. Then in this very small basic block, it's very hard to find independent instructions. So it's very hard to adjust the order of instructions. So this is the example. Even though the delayed branch is supported, and then the number of branch delay flag is 2, we cannot find any independent instructions before branch instruction. So which means the compiler needs to add loop after the branch instruction, because these instructions will be executed always. So if we cannot find any instruction that can be moved down to the branch instruction, then we need to fill this flag with loop. And then if loop is applied, so loop is executed, it's just the clock cycles are wasted. The performance is not good for this case. So that is so even though the branch delay slot is applied, it's not good for the performance. You can think. So this is the example code. So as you can see, this example code is the iteration loop, and then And then if a compiler analyzes this iteration loop, the compiler can know, oh, this loop is executed 1,000 times, right? But we can easily know. So, and then this is the compiled code. So load, and there's a load, add, and store instruction here, because this is the array is read, so array data is read from the memory. This is added into the variable data, and then it's stored to the another array. And then we need to use the BNE. So problem is that if a compiler wants to assign these instructions to this LIW hardware or VLIW hardware, how can you assign the instructions? Oh, we have one load and one store instruction. The problem is that, oh, this store instruction received result from add instruction. So, the pipeline stores are not supported by processor, which means that the compiler needs to add empty slot if the data dependency is detected. So what's the problem? Oh, load is in the first group, we need to assign the load here, the group 1, and then we cannot assign add the group after this load instruction. But the good thing is that this is the 1. So there should be empty slot here, the group 1, 1, 2, and then group 3, we need to assign add here. So we can now assign any instructions for some other slots. And then after add instruction, after where's the FPLU2. So we need to add 2 empty slots, empty group, and then it's a group 6. We can assign store instruction. And then, this server I is the independent instruction. So which means that we can assign maybe sub instruction maybe here, and then branch instruction here because the latency is 0. And then, this is the delayed branch, which means delay, which means so we can apply them. We can create delayed branch here. So we can apply sub here, and then we can assign branch instruction here. And then these 2 slots are executed always because 2 branch slots. So what's the problem? Because we cannot find many instructions in the base block. VLIW has many slots for execution, like 5 slots. But these slots cannot find appropriate instructions because base block size is small. So how can we optimize more? Loop unrolled. If this loop is unrolled, we can find more instructions. Like so this is the example of loop unrolling, and the loop is unrolled 7 times. So which means that if this loop is unrolled 7 times, we can find 7 load instruction, and then 7 store instruction, and 7 floating point add instruction. And after that, this offset of the branch offset is adjusted, so we can have only 1 sub instruction and the branch instruction. So loop is unrolled, we can find more instructions, which means that we can find more instructions that can fill the slots of VLIW. So this is the example. So this VLIW has 2 memory slots, 2 floating point slots, and 1 integer or branch slots. So load instruction. So there are 7 load instructions. So 7 load instruction fills the first slots like here, and then we can and then also the latency is important. So after this load instruction is executed at the 1 slot, the add instruction can be be assigned to the floating point instruction slot. So for this first load instruction, and then after one slot, then this add instruction can be executed. And then we have two memory slots here, which means that the add instruction of the second loop can be assigned to the second floating point slot. Okay, so we can assign here, and then after this add instruction, after some delays, the store instruction can be assigned. So if we have only one, this loop is not unrolled, then we have only one this load instruction, this add instruction, and then this store instruction. And then maybe the sub, because the sub can be here, and then branch can be here. So which means that we need the 6 instruction group to execute this iteration loop. But what is the peak performance of this VLIW? Peak performance is this VLIW can execute 5 instructions per clock, right? Because there are 5 slots here. But for this example, the VLIW consume 6 clocks, so which means that VLIW can execute the 30 instructions. So only if the loop is not unrolled, this VLIW can execute only 5 instructions, right? The 5 instructions instead of 30. Very inefficient. So actually, in order to increase the efficiency of the VLIW, then we need to apply more aggressive compiler optimization technique. So loop unrolling is the one of the examples of compiler technique. So if the loop is unrolled 7 times, we can find more instructions like here. So if you see that this example, so there are 45 slots here, and then we can execute how many instructions? 7 load, 7 store, and 14, and then 21 and 23 instructions. So efficiency is improved, like so actually it was 36 over 6. So we can improve the efficiency of VLIW with more aggressive compiler optimization. Okay? And what's the problem? So, but compiler optimization technique is, even though compiler optimization technique is applied, there are many issues. Like code size. Code size is increased because the compiler needs to generate more instructions, which means that the loop is unrolled, and actually this loop has only 5 instructions, and then if the out-of-order processor is applied to this loop, then out-of-order processor can find more instructions after the branch instruction. So, but this is the VLIW, so compilers can generate more instructions, and the compilers need to assign instructions to the obvious line, which means that the code size is increased. If the code size increased, then our code will occupy more memory. So, and then also another problem is that if we cannot find some instructions, then there can be many empty slots. You cannot fill every slot in the VLIW. And then register pressure. So actually, the compilers can only use the architectural registers. Then the number of architectural registers is fixed in the instruction. But if the loop is unrolled, then compiler needs to use more registers than the register pressure. It's a very critical issue. Binary compatibility. So binary compatibility means that, so I already explained that compilers need to know detailed architecture or detailed information of VLIW hardware, like this one. So for example, so this our code can be compiled by a certain compiler, like a VLIW1 for the VLIW1. So this is the binary file. And then this binary file can be executed on the different process like VLIW2. And then let us assume that this VLIW2 has some better process architecture. So like this VLIW2 has the most lessful integer or floating point, or something like that. Or some different VLIW has the less number of slots, like so for example, less number of slots. It's the more appropriate example. So for example, VLIW2 has the less number of slots, like one memory, and then one floating point, and then one integer per branch. What's the problem? The binary code, the compiled binary code is compiled for two memory slots, two floating point slots, then one integer. So this binary cannot be executed by different VLIW hardware. It's very critical issue. Binary compatibility. After the branch instruction, you can find many empty slots. It's a kind of, actually it's the same issue of the Thomas algorithm. So after the branch instruction, we cannot find more instruction. IFP. Okay. So VLIW is also kind of, actually we can use the very simple hardware, and then it can be very fancy hardware because it's very fancy idea because we can use simple hardware. And then recently, it's very difficult to build complex hardware actually. But with the VLIW, we cannot reach some peak performance of processor. So I think this is the most critical issue of the VLIW, the binary compatibility. So actually, so this is some kind of compiler optimization technique for the software pipeline. So we can apply software pipelining to generate the kernel of the compiled code. So what does that mean? So this is the example loop, and then this loop has only 3 instructions. So you can find the data dependencies here. Okay. So it should be STF40R1. Okay. Okay. So we cannot find a dependency here. So the dependencies between load and add, and dependence between add and store instruction. So for the first iteration, these instructions should be assigned to the slot like this. Like O1 is here, and then after 1 clock, or after 1 slot, the O2 should be located here. And then, so actually store instruction needs to receive a result from the add instruction. The O3 should be here. So if this loop is repeatedly executed, then we can assign different iterations like this after 1 clock, like here. So then for this loop, we can find all instructions, all 3 instructions, like So if you see this row, you can find that we have O3 here, O2 here, O1 here. Then we can use this row as the repeated kernel of this loop. So for example, this is O3, O2, O1. So we assign the O3 to this store instruction. O2 is to this floating point slot, and O1 this floating point slot. So when this loop is iteratively executed, then we can assign some different instructions here, and then we use this as the kernel. So after that, the VLIW repeatedly assign these instructions to the hardware. So what's the problem? So the loop is unknown. Loop is unknown, and then this is the kernel, and then actually the regardless of the some number of unrolling, then we can apply the same kernel after the some prologue and then epilogue part of the code. So what I want to say is that this loop can be unrolled 7 times or 10 times or 15 times, but regardless of this number of unrolling, we can apply the same kernel, and then this kernel will be repeatedly executed by the VLIW hardware. But the problem of the loop unrolling is register pressure. Okay, like here. If when the loop is unrolled, then we cannot apply the infinite number of architectural registers. So that's why you cannot unroll loop. But so we cannot apply the loop unrolling for some very large number. So, and then in order to solve this register pressure, then we can use the rotating registers. So we will learn about the rotating register later. And then this rotating register is very similar to the actually register renaming. So what does that mean? So this is also the compiler analysis. So if we just focus on this example, then we can know that F0 this is register. F0 is produced by load instruction, and then F0 is consumed by add instruction. So actually the lifetime, so this means that the value of the F0 will be maintained until the O2, right? So this is the lifetime of F2. And then after this O2, we don't need to keep this register, right? Do you understand? The register is this F0 is produced by load instruction, and then this register is consumed by add instruction. And then after that, this add instruction is not used anymore, right? So this is the lifetime of this F0 is from O1 to O2. So which means that the value of this register file should be maintained until O2. Then we can assign new value to F0. Understand? And it's the same to the F4. F4 is generated by add instruction, and then the F4 is consumed by store instruction. So which means that we need to keep the value of F2 until the O3. Then how about the next iteration? O1 is here, and then actually the original code is the load F0 and blah, blah, blah. But this O1 cannot use F0. Why? F0 is produced by O1, and then we need to keep the value of F0 until the O2. But O1 is here. So actually, we need to assign new register for this O1, like different register number, like F5, like some different number. But the number of architectural register is fixed. We cannot find some. It's not easy to find the available registers, architectural registers in this case. So the rotating register, which this is very similar to the register memory. Right? So it's like this. So this register is changed to the R1, 0, R1, RR2, or RR3. And then we can assign the different physical registers for this R1 or RR2 until the end of this lifetime of the RR1. So even though the architectural register number is the same for the different iterative number, we can assign the different physical registers. So this is kind of a register. This is because we have to keep the data of this register. Okay. So actually, the compiler optimization is also very complex. Okay. This is another case. So what's the problem? So this is another example of the problem is that, oh, this is the F0 here, and then F0 is consumed by add instruction. F4 is generated by add instruction, and F4 is consumed by multiply. But another problem is that this multiply instruction requires result from load instruction. But we can find this case frequently because usually the instruction requires multiple source registers. So we can find some dependencies like this. So which means that F0 is produced by O1, and then this F0 should be kept until the O3. How about the F4? F4 is here, and then F4 is preserved until O3. Okay? The problem is that for this O3, then you need to get the value from the O1, here, and then, but if we use the same register number, this O3 can be written by this O1. So which means that this O3 needs the F0 from the O1, and then also F4 for the O2. But if this O1 try to write the data to the F0 before O3 is consume the data, then we can some war hazard can happen in this case. Okay. So we need to avoid this case. And then this is the somewhat more complex situation. I try to regarding some register renaming. So actually, the compiler needs to analyze the lifetime of the register in this case. So we can apply the rotating registers like this. So this is the example of the rotating register. So when the loop unrolling is applied, actually, I assume that the compiler need to analyze the lifetime of the registers. So actually, instead of the architectural register number, compiler assigns the rotating register like RR0, RR3, RR4, RR6 here. And then these rotating registers are mapped to the different physical registers, like the P0 to the P15. And then by adding base rotating register number, and then by adding base of the rotating register and the number of rotating register, the processor map the rotating register number to the different physical register. Okay? But when we apply this rotating register number, then we need to know the lifetime of this register. So, which means that we can assign the F0 to the RR0, right? Then this F0 should be kept until the O2 here. So, which means RR0 can be assigned to the different physical registers, but until this RR0 is consumed by the final instruction, then we need to keep the value of RR0 here. Okay, so compilers assign the rotating register number based on the lifetime of these architectural registers. Okay, so that's why. So which why VLIW optimization technique is it's not easy. So because in the out-of-board processor, this register renaming is done by hardware automatically. Right. The hardware can find some available empty registers flat in the physical registers, and then the hardware assigns some architectural registers to the different physical registers automatically. But in the VLIW, the hardware does not rename registers. So compiler just assigns the rotating register, and then based on the lifetime of the register, the different rotating register numbers are assigned, and then for each iteration, this RLB is changed. So base of rotating register is just changed, and then rotating registers are assigned to the different physical registers. Okay. So this is the rotating register technique in the VLIW. Also, another problem is if we just see if we just use some different hardware, like let us assume that the new VLIW hardware has the less number of slots, like one row, one floating, and one integer, then we cannot find some one line kernel that include all instructions. So in this case, the kernel is organized across two instruction groups, like instruction 5 or instruction 6, because this VLIW hardware has less number of slots. So in this case, we need to generate the kernel of the software pipeline like this. Then the kernel occupies the two slots. So which means that this is the number of clocks for one software, one kernel, and then this one kernel consumes 2 clocks for the performance. So this is So based on the hardware configurations of the VLIW, then the shape of kernel can be changed. Okay. Okay, and then but also if the loop carried dependencies are observed in the iterative loop, then the loop unrolling is restricted. So that's another problem of the compiler optimization technique. So in this example, we can find the loop carried dependency. So what does that mean? If we use some statement like this, then we cannot find any loop carried dependencies. So which means that actually the statement in the loop can be unrolled without any restriction. So which means that actually this statement can be executed in parallel. Okay? Because you cannot find any dependencies between different iterations. But if you see that this code, AI2 is updated by AI. So which means that you cannot, then this AI2 is consumed by AI. So in this case, there we can find some dependencies between different iterations. So in this case, the loop unrolling is restricted. So compilers can analyze this loop parallel dependency with this graph, like here. So this is the compiled code. You can find that in this code. Oops. So these are iterative instructions from O1 to O5. So you can find some loop carried dependencies here from O4 to O1. Then we can make some graph like this. So and then each edge of the graph labeled with some this deep and minimum number of clocks. So then each edge have some label like this. So deep is the number of iterations between the two operations, which means that we can find the loop carried dependence between O1 and O5, O4, not O5, O4. So this is the number of iterations, the difference of number of iterations between two operations. Also, we can find some clock delays between instructions. So this is the later number represents the minimum number of clocks between two instructions. And then based on this information, compilers can generate the instruction groups like this. Okay. So because of the loop carried dependency between O1 and O4, for this iteration number 3, O1 should be located after O4 here. Okay, if O1 is located before this O4, then O1 will have wrong value. So because of loop carried dependency, O1 should be here, and we can assign the different instructions like this, O1, O2, O3, and O4 here, and based on the number of clocks between two instructions. So we need to set some empty slots between O1 and O2 here, and then empty slots here and here. And then O1 of the iteration number 3 should be located after O3, O4. And then if you generate the software pipelining with this kernel, then this becomes the kernel of this code. The problem is that this kernel includes the many empty slots. And then in order to execute this kernel, then VLIW need to consume witchcraft. Okay? But because of the loop carry dependency, then we need to generate the software kernel like this. So this is another disadvantage of the VLIW, which means that it's very hard. So actually, loop learning is the main feature of the compiler optimization, but loop learning cannot be applied to every all type of loops. And then if the loop carry dependency is observed, then the loop learning is the restricted, and then we need to generate the kernel of the software pipelining based on the loop carry dependency. Okay, so I will stop here. So but you need to remember that. So actually, in the next class, I will cover some additional some techniques of the VLIW, and then I will cover about the microprocessors and GPUs. So just remember that VLIW is the new type of processor, and then the burden of the hardware part is moved to the software part, like compiler. So compiler needs to analyze the some code structures and then instructions, and then compiler needs to apply some optimization techniques by adjusting order of instructions and then loop learning, progressive optimization technique. Any questions? So I stop here, and thank you for your attention, and then see you in the next class.